Okay, today we've got a rather long chapter, the chemistry of carbon, but I think we can fit everything in. I want to talk about two parts. Part A deals with organic chemistry and some of the terms that are used. We'll talk about hydrocarbons and other kinds of organic classes, what they do, what their structures are. And then we'll move into a brief overview of some terms in biochemistry and nutrients in food, look at minerals, look at vitamins, carbohydrates, fats, and lipids, and then we'll look at steroids. So here we go. Organic chemistry is basically the chemistry of carbon compounds. Biochemistry is the chemistry of compounds in living systems. Now, there's some overlap because many of these compounds are primarily carbon compounds. Up until the early 1800s, living systems were thought to contain a vital essence of some sort that made their chemistry different. Friedrich Wöhler in 1828 made urea, which is produced by the body from inorganic materials, and began to challenge this idea of a vital essence. Organic compounds always have carbon as part of the molecule. They almost always have some hydrogen atoms present also. Some molecules will contain oxygen or nitrogen, and sometimes both. Now, most of the other elements aren't involved. This is why organic chemistry is so much fun. Their periodic table is much shorter than everybody else's. The atoms in organic compounds are generally joined together by covalent compounds. Two atoms sharing electrons. These bonds are more stable, a little harder to react. Isomers are molecules with the same atoms, but they have different structures, and we'll illustrate that. Functional group is a specific site on a molecule where reactions can take place, and we'll show you some of those. And the parent molecule is the starter molecule, and on the parent molecule you build more complex molecules. Okay, here's an example of some isomers, molecules with the same atoms but different structures. 1-butene and 2-butene, for example, both have 4 carbons, both have 8 hydrogens, but they are structurally different. And here's a couple of more, much more different. Ethanol and dimethyl ether each have 2 carbon compounds, 1 oxygen, and 6 hydrogens. But they have very different properties in terms of being liquids or gases, solubility in water, reactivities, other things. Okay, here are the primary functional groups in organic chemistry, and you can find illustrations on pages 150, 151 of your text. The purpose behind a functional group is to identify a specific structure that will undergo some kind of a reaction. Now, alkenes, alkynes, and alkanes are hydrocarbons. The alkanes have all single bonds. The alkenes have a double bond, and the alkynes have triple bonds. The alkenes and the alkynes will be much more reactive than the alkanes. For example, here's an alkene addition reaction using propylene and hydrochloric acid. The hydrochloric acid adds across the double bond. The hydrogen goes to one carbon, the chlorine goes to another carbon, and you form a chloroalkane. So this is a general reaction for alkenes, and anytime you see an alkene, you can carry out this reaction with it. Formation of an alkene from an alkane. You can heat and take out the HCl and form a carbon-carbon double bond and a hydrochloric acid. Aromatic compounds are interesting. They originally called that because they have somewhat of a pleasant odor, and they have an interesting structure with a pi bonding cloud above and below the ring, and this is why they're quite often represented as the benzene structure is, not with alternating carbon-carbon double bonds, because that doesn't really represent the structure, but the six-sided compound with the ring in the middle. Alcohols, variety of different alcohols. They have different shapes, different structures, but they all have the OH group on them, and that's what makes them an alcohol. Aldehydes have a functional group with a carbon-oxygen double bond, the hydrogen on the carbon, and another group of some sort. And here you can see different aldehydes. Notice that they all have the carbon-oxygen double bond and a hydrogen. Now, ketones, on the other hand, have the carbon-oxygen double bond, but they have two groups attached to the carbon. They do not have a hydrogen attached to that carbon, but they have two groups, and so that's the difference between the two. And in general, a lot of the reactions are quite similar. Carboxylic acids have the C double bond O, OH. That's a characteristic of carboxylic acids. That's their functional group, and when you're doing reactions, that's a group that would react. Esters, similar to carboxylic acids because they're formed from carboxylic acids. Esters are actually the product of a carboxylic acid and an alcohol. Now, when we talk about functional groups, this allows us to focus strictly on the functional group and the reagents, and we don't have to worry about the rest of the molecule. For example, if we react this tertiary butyl alcohol with concentrated sulfuric acid and heat it up, we're going to form a carbon-carbon double bond and a molecule of water. So any alcohol is going to do this, so we don't have to worry about what's hanging off on it. We just worry about the functional group itself. Likewise, an ester, carboxylic acid plus an alcohol will form an ester. The R groups can be pretty much anything. The important thing is the carboxylic acid functional group and the alcohol functional group to show the reaction between the two. Okay, what's biochemistry? Biochemistry is the chemistry of living systems. It comes from a word bios, meaning life, so means the chemistry of life systems. And it's the study of chemicals and chemical processes that make up life. So what we'll look at in this chapter very briefly are the different chemical classes needed for healthy living. And we'll take a look at some of these. Chapter 10 also describes some biochemistry processes, but that deals with some of the large molecules that are involved in maintaining life and allowing cells to reproduce. Many complex reactions are needed to change food into useful materials and energy, and these reactions are important for biochemistry and important for life. Now, we look at minerals in the diet. They exist as ions. They don't exist as elements, but they're ions. Sodium plus, calcium 2 plus, chloride minus. They're primarily cations, sodium, potassium, calcium. There's a few anions, mainly phosphorus and chlorine. They're needed for a variety of body functions. We're not going to have time to go into all of that, but it would be a few lectures in and of themselves. Now, mostly you can find them in the diet. Generally speaking, people don't need supplements to get minerals in the diet. And there's some more information, table 8.7, pages 166 to 167, to take a look at and get more detail. An excess of a mineral can create problems. You can make yourself sick by taking too much of a supplement, which is why supplements have to be approached very carefully. Now, these are some of the minerals in food: calcium, sodium, magnesium, cheese and milk, cobalt in milk, cobalt in, looks like a good steak, sulfur. These are all mineral food. Vitamins are important. Vitamins help biochemical reactions to take place. They play a very important role. They serve as coenzymes often. A coenzyme helps an enzyme carry out a reaction. So if the coenzyme isn't there, the enzyme can't do its function. They have very complex effects on body chemistry. You can't say this vitamin does this. Vitamins do a lot of things. Now, again, you can get all the vitamins that you need in a healthy diet. The problem is a lot of people don't eat a healthy diet and may need a supplement. There are some problems with vegetarian diets, both in terms of vitamins and other types of materials that are consumed, but vegetarian diets quite often do not have all the vitamins that you need. You can overdose on vitamins, just like you can overdose on minerals. You can get skin problems, your vision will be blurred, you can have heart problems, you can have liver problems, so lay off the supplements unless you really have to have them. Okay, let's look at some of the different food groups. Carbohydrates comes from the words for carbon and water, and you look at the structure of the carbohydrates and you can see that. They're essential for many biochemical processes. Carbohydrates primarily are taken in through the diet and the body uses them. They're made in our bodies by a process called gluconeogenesis. Gluco for glucose, neo new, and genesis formation. So it's the formation of new carbohydrate molecules. Plants make carbohydrates using photosynthesis, and then we eat the plants and we get the carbohydrates in our diet. Simple sugars, triose, tetrose, pentose, and hexose, these are the classes. They're named by the number of carbons in them, and we primarily worry about the hexoses in our diet. Complex carbohydrates are composed of more than one carbohydrate molecule. Disaccharides composed of two hexoses, and there's a couple of them listed: sucrose, table sugar, lactose, and milk. Polysaccharides composed of many, poly meaning many. Starch and cellulose are two polysaccharides. They're two different configurations, even though they both use glucose. Both types are used for food. Disaccharides and polysaccharides are used for food. Fats and lipids both refer mainly to the same compounds. The triglycerides are a primary dietary source of fats, and these materials are stored until the body needs energy. Now that means if you're not out working and being active, they are stored and stored and stored, and we don't always like that. They also serve as insulation for the body to cut down on temperature loss. They serve as padding for the organs. They protect the organs from shock. They're important parts of cell membranes to keep the cell intact. Different kinds of lipids, saturated lipids and unsaturated. The unsaturated have double bonds in them and their properties are different. They're supposedly not as healthy for them. Steroids are involved in cell membrane structure, and a number of hormones are steroids. Estrogen and testosterone, the female and male sex hormones, are steroids. Bile acids are a form of steroids and they help digestion. All steroids are made of cholesterol. Cholesterol is the basic molecule. It would be the parent or the starter molecule. And here's some structures. You can see the cholesterol in the white image, and then you can see some structures of different hormones that have that basic cholesterol structure in it. Okay, we've talked about organic chemistry, we've talked about what isomers are, the importance of functional groups, the classes of organic compounds, we hit these very, very briefly, and how to sort out organic reactions by looking at the func groups. In biochemistry, we discussed what biochemistry is, the nutrients that we find in food and their importance, the minerals, the vitamins, the carbohydrates, the fats, the lipids, and the steroids. All of these are important components in our diet. They all serve a variety of very complicated functions, and they're all very important for us. So that's it. Thank you for listening. I know this has been a fairly fast run through, but I think that you can handle it, and I think that you can get some good material out of the textbook. So we'll talk to you later. Bye-bye.